Assalamu alaikum. My name is Abdullah Rushid Samir. I will be presenting about the gradient descent of in machine learning. My ID is 12008003. In f- uh, analogy, let's talk about some analogy about gradient descent. Imagine you are lost in a dense fog. Imagine you are lost in a dense fog in a hilly landscape. Your goal is to reach the lowest point in the valley. You can see the entire landscape, but you can feel the slope ground beneath you. My question to the audience is, how would you navigate to the lowest point? You do not have any other senses, and what would be your strategy based on what you can sense locally? Answer is quite simple. Exactly, most of us would likely feel the ground by sloping downwards and take a step in the directions. We might take small steps to avoid overshooting if the slope changes suddenly. The intuitive approach to of following steepest descent is the core idea behind our algorithm gradient descent. Now we want to connect this analogy to our machine learning. Just like our Foggy Explorer, the machine learning models often need to find the lowest point in a complex landscapes. In their machine learning, this landscape represents the loss function which measures how poorly our model is performing. The loss points corresponds to the optimal set of parameters that minimizes the loss. And the question to our audience is, what do you think the slope of the ground might represent in the context of loss function and model parameters? The slope of the ground in machine learning is analogous to gradient of the loss function with respect to some model's parameters. It tells us how much the loss changes if we make small adjustment to each parameter. It also indicates the direction of the steepest increase in the loss. In case of we do not know about what is loss, how we calculate loss, we have to know our actual values, then we predict some values. We give we give loss according to our actual values and our prediction values. and we all know gradient descent is an algorithm. That strategy of our explorer, that we said earlier, the strategy of our explorer might use the filling of the scope, taking the steps in the direction of the steepest descent. Is precisely the core idea behind gradient descent. It is an iterative optimization algorithm that helps model learn to gradually adjusting their parameters. What another question to our Another question to our audience is, what do you think the steps our explorer takes correspond to the process of machine learning model learning? Basically, the steps our explorer takes are like the small adjustments the machine learning model makes its parameters. In each steps, the model aims to move closer to the set of parameters that result in minimum loss, meaning better performance. Key concepts in our gradient descent algorithm, there are four key concepts: parameters, loss function, gradient, and learning it. Parameters, these are the knobs of our model that we take to make our predictions. Loss function, with this function quantifies error between the model's predictions and the actual values. Gradient, this is the vector of partial derivatives of loss function with respect to each parameter. It points to the direction of the steepest ascent to the loss. Learning net, this is crucial hyperparameter that determines the size of the steps we take in opposite direction of the gradient. Another question to the audience: why do we move in the opposite direction of the gradient? What would happen if we move in the direction of gradient? We move in the opposite direction of the gradient because the gradient tells us why is the loss is increasing most rapidly. Our goal is to decrease the loss, not to increase the loss. So we take steps in the negative gradient direction. If we move in the direction of the gradient, we will be making our model perform worse, increasing the error. It means we're going uphill instead of going downhill in our quest to find the uh, downside of the hill area. So next we will be talking about the iterative process step by step. Gradient descent works through a repetitive process. Initialization. Start with an initial guess for models parameters. We calculate and compute the gradient of the loss function with respect to the current parameters. We adjust the parameters by taking a step in the negative direction of the gradient scaled by the learning net. Repeat. Continue the steps 2 and 3 until the stopping criterion is met. The loss function is sufficiently low or maximum number of iteration is reached. Maximum time we stop when the loss is sufficiently low. And another question to our audience: what are some potential challenges or consideration when choosing a learning net? What could happen if we choose too large or too small of a learning net? The learning rate is critical. If it's too large, the steps we might take be so big that we overshoot the minimum, potentially oscillating around it, even diverging away from it. If the learning rate is too small, the steps will be tiny and the learning process could be very slow, taking a long time to converge a good solution or even getting stuck in a shallow part of the Lord's landscape. Next, we would try to visualize our gradient descent. Gradient descent, visualizing gradient descent. If you want to visualize gradient descent, we want to visualize a hill or something have a steep curve in it. If we like in the pictures we are showing, there are many variation gradient descent. Some gradient descent variations are batch gradient descent, stochastic gradient descent, SGT. We use it with our mm, uh, other classification algorithm like SBM, SGT algorithm, stochastic gradient descent. We use with SBM and mini batch gradient descent. So if you following uh, that now, though we have another question for the audience: what are the trade-offs between the different variation in terms of computational cost and convergence variance? Like we have discussed three kind of different techniques in gradient descent. What are the trade-offs between them? Batch gradient descent can be computationally expensive for large datasets as it processes everything at once. The gradient estimates is more accurate, leading to potentially more stable convergence path. A stochastic gradient descent is much faster per iteration because it only takes one data, making it suitable for large dataset, but its convergence is often noisy due to its randomness. Mini batch gradient descent offers a compromise, providing a balance between computational efficiency of SGT and more stable gradient estimates of base gradient descent. What are the challenges and consideration? While powerful gradient descent isn't always straightforward, we need to be mindful of local minima. The algorithm might get stuck in suboptimal value. Saddle points. Flat regions in the loss landscape can slow down the learning. Learning rate tuning. Finding the right learning rate is very important. Feature scaling is the scale of features can significantly impact the convergence. Another question to our audience: can you think any techniques or strategies that might help mitigate these challenges? The to tackle some of the to tackle some of the challenges, we can like local minimum. We might use the techniques like momentum, which all also used in stochastic gradient descent gradient descent algorithm. Momentum, which helps algorithm to route out the shallow valleys or try different initialization points. Momentum can also help navigate settle points. For learning rate, for learning rate tuning, we can use learning rate schedules that adapt the rate during training. Feature scaling. Feature scaling is crucial for ensuring that all features contribute equally to the gradient and prevent some features from dominating learning process. There can be many features in in our dataset, but not every feature is as important as other features. So we have to select our features very effectively. More advanced optimization algorithms like ADAM or RMS Pro also incorporate mechanisms to address these challenges. Again, conclusion and of power of iteration. Gradient is in its various forms is cornerstone of modern machine learning. Its iterative nature allows models to learn complex patterns from data by gradually refining their understanding of underlying relationships. It's a beautiful example how a simple intuitive idea can lead to incredible powerful results. Thank you. That that is for presentation.